The next thing we'll discuss is the idea of the interior of an angle. We start by assuming we have a non-degenerate, non-straight angle, ABC. We denote the interior of the angle by this int, angle ABC. So what exactly is the interior? The interior is the set of all the points that lie on the A side of line BC and on the C side of line AB. So here I have a picture of my angle and the lines BC and AB. I start by the set of all points that lie on the A side of line BC. So the A side would be this side over here. So all of the points over here. At the same time, I need everything that lies on the C side of line AB. That would be up here. So the actual interior of the angle would be where they overlap, throughout here. My definition of interior did assume that I had a non-degenerate, non-straight angle, so let's talk about what happens in those cases. If angle ABC is degenerate, which as a reminder, that means the measure of angle ABC is equal to 0, then the interior is just the empty set. On the other hand, if angle ABC is straight, which means that the measure is 180 degrees, then the interior is actually the whole plane. It's both sides. What about in spherical geometry? So here's my sphere. I have one ray here that's H. And then another ray that's K. So I have my angle. In this case, the interior would be this piece right here. It's where the two hemispheres are going to intersect. And this is known as a lune. And it's always the smaller of the two intersection pieces. So I do have this highlighted section as intersecting, but also have the entire outside and back of the sphere. So we do pick the smaller of these two pieces. So I want to be able to say that if I have a ray that's on the interior of an angle, then that ray is between the other two. However, so far we don't have anything that will allow that. And so we're going to do this with Axiom 10. And this is known as the angle addition postulate. We start by letting D be a point in the interior of angle ABC, or a point on one of its sides. Then I have that the measure of angle ABD plus the measure of angle DBC is equal to the measure of angle ABC. So to demonstrate this idea, I have this angle here, ABC, and I'm going to pick some point D in its interior. And I'm going to consider these angles. Then I have that the angle ABD plus the angle of DBC is equal to the whole thing, ABC. And this would give me that ray BD is between rays BA and BC. Next, we'll look at something called the linear pair theorem. The linear pair theorem says if I have two rays, H and H prime, that are opposite, and K is any other ray concurrent with H and H prime, then I have the betweenness relation H, K, H prime, and HK plus KH prime is equal to 180. So here I have a picture demonstrating this idea. I have my opposite rays H and H prime, and I have that K is another concurrent ray. Then we have HK, H prime between this relation, and the angle HK plus the angle KH prime should be equal to 180. And this is going to follow pretty quickly from my Axiom 10. The interior of a straight angle is actually the entire plane. So my ray K definitely passes through an interior point of my angle HH prime. So by my axiom, this must hold.